Woohoo! 150 IQ, let's go! Remember, all are welcome, even if it's the case of enjoying vibes. You know what, Zir? Thank you. Thank you for expressing that. And it's absolutely true. Everyone is going to be welcome in today's lesson, even if it feels a little bit more advanced than usual. I hope I don't lose all of you. And it's okay to not get these things. This is hard. And I haven't touched this in 10 years, so I'm going to probably make a few mistakes today. Bear in mind, I would like to wholeheartedly and in hindsight apologize for this lesson. This is going to be a learning stream for me too. I haven't taught this. This is going to be new teaching for me. There's going to be concept that I might have forgotten. I have a few stories and stuff to start with. So yeah, let's start the lesson, shall we? I have a lot of plans today. I was wondering, should I stop God of War? Do you know what, Nat? We're going to play a new game today. I was going to say maybe I should kind of finish up God of War, but I am thinking about Steam achieving God of War off stream. I'm downloading it on my Steam Deck. I think I'm just going to play God of War off stream. If that's all right with you, I don't tend to do 100% on stream. It's not something that I enjoy. I don't do speed runs and stuff like that. I do it personally, but I don't do it on stream. I don't do many achievement hunting stuff. And usually when I do achievement hunting, I have to concentrate. And it's not an entertaining stream. So if it's all right with you, I finished the story of God of War. And I'm going to do the rest of it off stream. All the side quests and just kind of chill. Will that be of your yeah, spin the wheel. So I might pin it in the chat now. We will do spin the wheel at 16:30 for spin the wheel. If anyone wants to be there. So we'll do spin the wheel today in half an hour. Wouldn't it be fun to do a physics experiment where the outcome determines the game? Girl? That's not a bad idea. But what kind of experiment do we do that we don't know the prediction of? You know? Usually all the physics experiments you do is a verification experiment, unless it's a brand new one. Actually not a terrible idea, though. Can't be an entertainer and a speedrunner at once. I mean, you see, the thing is, speedrunners are a type of stream. Does that make sense? It's a type of content you create. My content tends to be education. Stupid. Me just being stupid, you know? And my reaction to playing games for the first time. I think that's kind of like a mix of what I tend to do. That sounds a bit dodgy. I think we had a nice conclusion yesterday. I agree. It was a nice story conclusion yesterday, and then I'll just play the rest of the side quests off stream. I think that's a good way of doing it. Okay, so in half an hour we'll do voting for the game. So let's concentrate really, really hard for half an hour. Let's make our brains work. Okay, chat, everybody massage your brains. Today we are going to do quantum theory. Okay, so we need our brains in a quantum state, chat. Are we ready? Let's go. So I'm going to start for our first few minutes of talking a little bit about the history of the atom. Okay, and many civilizations around the world had explored the idea and the concept of atomic theory way, way, way before it existed, but it wasn't agreed upon. So there was some ideas possibly in ancient Greece. There was a good few in, I was going to say ancient India, but I don't think that's the right terminology. There's a proper term for that. But there was basically, what I want to highlight is that around the world, people had notions and commentary of atomic theory, that things were made of atoms, but they were so small that we couldn't see them. But most people kind of didn't vibe with that, is the brief summary of it. There was this whole idea of the plum pudding model, where, who was that again? The plum pudding model again. Oh, what's his name? To say his name. Oh, no, it doesn't say his name here. The guy before Rutherford, exactly. Who's the guy before Rutherford? His... No, Bohr's way after. Bohr's quantum. Let me think. God damn it, Nathan! Who came up with the plum pudding model? Plum pudding. Thomason, thank you. God damn it. It was J.J. Thomson. God damn it. Completely forgot. There we go. There we go. Chat jumped in. Perfect. So yes, so he came up with this idea of the plum pudding model, and with the idea that you get a bit of dough, plum pudding. I actually don't know what plum pudding is. Apparently it's pudding, and I'm guessing there's plums in there. You get a little ball, and in there are embedded little balls of positive charges, and around that, and some negative charges. So they knew that atom existed of positive charges and negative charges. More than likely, most of the time, they were neutral. And then if you did like weird static electricity stuff to them, they would build up charge in one side or the other, and it would explain ions and so on and so forth. But at the time, didn't really know too much about it, kind of accepted it, went along with it. Great story. Oh, imagine a plum pudding model as a watermelon. That's actually good. That makes sense. And the seeds are the electrons and the protons then. Well, ultimately, it doesn't matter because it turns out it wasn't true. And the guy that we give credit for discovering the truth behind this is probably the most famous New Zealander scientist ever in history. He's on the money in New Zealand on the, what is their currency called? I think it's called the dollar, but what term comes before it, I'm not too sure. But he... the name is Rutherford, right? Now, he's given credit to the experiment, and this is where things get iffy if he deserved the Nobel Prize for his discovery on this. So some people claim that he doesn't deserve the Nobel Prize because it was a student who performed the experiment. However, if you believe the story, I haven't done my own research on this, so I can't say too much on this. But if you believe the story of what the events had happened, was that when Rutherford was looking at the results of his PhD student at the time, he came up with the idea himself, and I believe it was Geiger who was looking at the results, told him, I need you to change where your sensor is. I want to see what happens on the other side of the detector. And so the student did that and recorded results, and then came the atomic theory that we know now, where atoms are mostly made out of space and the center is positively charged. That was the consequence of the gold foil experiment by Rutherford. So you come up with it yourself. Who deserves the Nobel Prize? Would it be Rutherford or his student? It can be quite heated for sure. We needed drama YouTubers back then. Is that a model of demon core? Yes, it's a real model of a demon core. The size is correct except for this part because it's too big. And it like blows up and goes radioactive and stuff if I scream too loudly. Hi, Preserve. Welcome in, welcome in. Okay. So.
And they call it a mine.
A mine. Thank you so much for the 13 months. Thanks, mate. Great question. Should they have shared it? I suppose the question comes in the level of the Nobel Prize that was given. Does the student deserve it? I'm not sure. I don't know if he won the Nobel Prize by himself. I wonder if he shared it, because you can share it up to 2 people. So maybe the other 2 people did something more. I'm not sure about that. But Rutherford was the famous guy who said the famous quote. What did he say about chemistry and physics again? Everything in the world is physics. Sorry. Everything important in the world is physics, and everything else is just stamp collecting, says the winner of the Nobel Prize for chemistry. That's the running anecdote, the running joke. Hey, thank you again so much for the 13 months. Well, instead of calling it the Rutherford model, most people refer to this model as the planetary model, because it kind of looks very similar to the way planets operate. So with that, I'm going to start drawing a few diagrams for you. Go up, chat. Knocked you over, guys. Apologies. Let's do things here with my spray bottle. Chemistry is basically physics in water solution. I really think that chemistry is just a model of physics. If you really look at most of the things that is done in chemistry, it's just a model. It's just a model of physics. That's why, the joke is that people in chemistry, there's a rule. They'll talk about a rule, but only 3 atoms follow that rule, or something silly like that. Well, the anecdote comes from exactly that reason. It's just models. It's just different expressions to make things really nice and straightforward. Which makes me think and reflect on a lot of things in biology that I studied and other subjects, engineering and so on and so forth, that really everything is just a model of physics. Everything is physics. That's where I get my pretentious snobbiness, that everything is physics and you're all physicists. Every single one of you lab rats right now are physicists. Physics Nation, yeah, let's go. So, let's look at the planetary model. Oh, this needs to dry. While that's drying, let me just wipe down this part as well. Might as well get a nice clean board. I should have started that with the stream. Or sorry, I should have done this earlier. Okay, here we go. Let's have a quick look at a few things here. Digital background when tofu. So, the planetary model describes atoms like this, where you have the positive charge in the center and the electron orbiting on the outside. Kind of fair. Sorry, I don't know if the mic was picking it up. Positive nucleus in the center and an electron orbiting on the outside shell. And it orbits around kind of like the moon is orbiting our planet Earth. I was about to say our planet Earth, and I thought, wait, Earth's not a planet. Why would I say that? I had a whole conversation in my head there very, very quickly. But yes. Now, if you remember your centripetal acceleration laws, right? So centripetal acceleration is towards the center of the proton, right? So the electron is being pulled into it due to electromagnetic attraction. But it also has a huge velocity. The electron has a huge velocity and is traveling perpendicular at any given time. That's its V. That's its A inwards. So the force, the centripetal force, Fc in this case. Hi, Chris Matt, welcome in. The centripetal force then is mv squared over r. Okay? So that is the force that is experiencing, I'm not in a category? Oh, you're right. Thank you so much for letting me know. I didn't even know you couldn't be in a category. Fascinating. Cool. Hi, Krishna. Welcome in. Thanks for letting me know. I put myself in silent. I didn't even know you couldn't be in a category in Twitch. I thought you had to be. That's so unusual. It's the Wild Wild West out here. Exactly. But thank you for letting me know. So the centripetal force experienced by this electron's inwards towards the center of the nucleus is its mass times its linear speed, which is perpendicular to the centripetal acceleration. Perpendicular means at a right angle to it, with its linear velocity v. mv squared over r. Hopefully we're on board with this. I kind of covered this before a long time ago. It might be a little bit of revision, but just take my word for it if we're a little bit confused or whatnot. Now, there's another force equation when we talk about stuff. Maybe this is going to seem familiar to you. K times Q1, Q2 over R squared. Kind of looks like the gravitational law, but is not. This is Coulomb's law. Okay, so Coulomb discovered this a long time ago. K is Coulomb's constant. It's 9 by 10 to the power of 9. Q is the charge of one particle. Q2 is the charge of particle 2. And R squared is the distance between the two particles. So what this expression shows, or what it calculates, is what is the force experienced by two charges existing in this plane, if that makes sense. So if I have a positive electron and a negatively charged electron, wait, if I say it's a negatively charged electron, does that mean it's a positron? Am I being descriptive of the electron? Or am I clarifying that it's a positron? I mean, it's kind of like saying, I was going to say white snow, but can you say that? You can say an electron is negatively charged, but can you say a negatively charged electron? Do you know what I mean? I don't think you can say that. How to break a physicist? Just let them talk. They'll do it to themselves. It's not though. If you think about it, an electron is negatively charged, and a negatively charged electron is technically. Because that second statement states that you're describing the state of the electron charge, the charge of the electron, which otherwise wouldn't be known. But if you know that the electron is negatively charged, then the double negative makes it a positron. Yeah, like mathematically it would be a positron, yeah. Anyways, it's fine. Sorry. It's redundant. It is redundant. Fair enough. Sorry, I got distracted. Anyways, this is Coulomb's law. You have Coulomb's constant, the charge of Q1, charge of Q2. So you have negatively charged electron. You have a positively charged positron, or a proton. And so That'll be the charge of 1.6 by 10 to the minus 19 for the electron, 1.6 by 10 to the minus 19 for the proton. The distance r squared is the distance between them to be squared, okay? And so you can calculate quite literally the force of attraction between the proton and the electron. However, if you had two electrons instead, it would be the force of repulsion between them. Because remember, like charges repulse each other and unlike charges attract each other. That lovely figure of speech that they use in the English language, opposites attract, come from this statement. Traveling backwards in time. Okay. We only have 15 minutes left before we're doing spin the wheel. Again, we'll cover more physics later, but we are going to be doing spin the wheel. So in this case, this would be a proton. I'm just going to replace number 1 with P. And I'm going to replace number 2 with E. So proton and electron. Because in the case of our atom, we have an electron orbiting around. It's an electron, and the positively charged particle is a proton. Hi, Glorixy. Welcome in, welcome in. Yeah, so it's an interesting thing that you point out, Conrad. When we draw electric field lines in physics, and this bothers me, and I don't know why it bothers me, because we always take positive to be positive, or, you know, it's a weird thing. But when we draw an electric field line in physics, it's what would happen if we placed a positive test charge in that place. What would happen to that positive charge and which direction it will go. But in my mind, because when we deal with that kind of level of physics, the most basic charge is always an electron. We tend to deal with electrons, right? Electrons is the recipe of life. It's water when it comes to quantum physics. You use water for everything in chemistry, in other fields of physics and whatnot. And the water for quantum is the electron. And so you would think that it'd be the electric field lines will always express what the electron is doing, but it's actually the exact opposite. So it's in the opposite direction. Anyways, that's just my little rant there, but just to be aware of that. Well, they're using a positron, exactly. So the charge of the electron is equal to minus E, while the charge of a proton is plus E. The symbol for an electron is just letter E. And so we're going to use the sign positive afterwards to dictate that it is a proton, and a negative sign to dictate that it is an electron. Is this nuclear force? No, this is not nuclear force. This is Coulomb's law. It's the it's called the electrostatic force as well. So that's what it is. Not nuclear force yet. Now, something that I'm going to do is I'm actually going to drop the negative and the positive sign, generally speaking. And the reason is because we don't care about direction here. We're trying to calculate magnitude. Keep that in mind. So because we're keeping track of magnitude, we're not going to keep track of the sign. Just bear in mind that with positive nucleus, negatively charged electron, it is attracted to it, but it's moving so fast it's spinning out. There we go. Yeah, exactly, mate. Probably more than likely that. So something that we can do is, well, we can equate this to this. The electrostatic force should equal to the centripetal force in this case. So let's sub in all our values. That's K, electron charge 1, electron charge 2, positive sign, not squared, all over R squared is equal to mv squared over R. There's a few things that are similar there, or at least one thing that I can see that's very similar. One of the things that we can do is we can knock off one of the R's. Get rid of that squared, get rid of that R. Exactly, we can get rid of those R's. Sure, I did that right. So it's the force of attraction between them and Conrad. So what I would say is that even though they're different concepts, they still have to equate with each other. All of these laws of physics still have to be obeyed. So if that's the force of attraction via electrostatics, this has to be, and this is the balancing aspect of it, then that balancing electrostatic has to be the centripetal force that's balancing it out that we were discussing earlier. I don't know if that's very, very helpful, but they are the same force technically. We have expressions depending on what we need, but they are the same thing. Let me try and think of it another way. It's kind of like using two different equations, but they're the same really. Let's say you take something like the ideal gas law. There's the physics version of it and the chemistry version of it. The constants all change and everything's a little bit different, but in reality, they are the same. No, it's okay. You know what? If you're not convinced, that is completely fine. I'm not taking any offense to this. What I'm teaching today is this is a big jump to what I usually teach. I'm going to try and be slow about it where I can, but there are going to be moments of, Tofu, I don't believe you, but I'm just going to ask you all to trust me. So we're trying to see that electron circular motion. Yes, exactly. That's what I'm going to show, hopefully, Glorix. I'm going to show the flaw in Rutherford's model and how quantum physics steps in and saves atomic theory. Basically, quantum physics had to be invented to fix this, what I'm going to show you. I'm going to show you the problem first. What time is it now? It's 6:20. I'm going to focus on creating the problem. We're going to do spin the wheel, and then I'm going to spend the rest of the stream fixing the problem. Sounds like my life. Here we go. So let's rearrange the equation. We want to get v squared on its own. So v squared is equal to a 2e over mr. Oh, not 2e. Sorry. E squared. E multiplied by e is e squared, not 2e. Whoopsie daisies. Now, one of them is positive, one of them is minus. We don't care. We're caring about the net charge, the magnitude of the charges themselves. Problems are fun when you can solve them. Exactly, exactly. It is really fun, though, to solve problems. I don't know. I think that's maybe the true birth of me being a physicist today, is when I was a teenager and I was doing applied maths or just difficult maths. And that feeling of when you solve something, especially when you were struggling, oh, it's so worth it. And I get that feeling sometimes with programming. I hate to admit it, but sometimes with programming, I get that feeling where I'm stuck on a code for like hours and then you fix it and you get this moment of satisfaction, like this is the reason I live for. And you chase that high for the rest of your life. It's way better than drugs or alcohol. I wouldn't know. But it's way better than that. Don't do drugs, do maths. Way better high. Hi, Daniel, Loki. Welcome in, everyone. Aso. What is the fundamental area? Classic physics, I would say. I think finding a first year textbook is really, really great. And usually people start in mechanics. So an introduction level to physics would be mechanics. It is a bit boring, but it is needed. I'll be right back, chat. I'm actually quite thirsty. I'm talking so much shit. I'm just going to grab a bottle real quick. In a panic, I couldn't find a bottle. I just got a glass of water. Definitely more healthy, at least. That is true. That is true. Okay. So, we have an expression, and someone mentioned it, I think, is that we can get rid of that squared over here. If we want to get rid of the square over here, we're going to root all of this. So we put all of that under a square root. Now, this is interesting. I know what the Coulomb's constant is. I know what the charge of an electron is. We know what the radius of the atom is in this case, if we had known, if we wanted to measure. And we know the mass of an electron. Hold your horses. We could calculate the speed of the electron. All of these parameters, we can absolutely calculate the speed. Now, I have the answer here so I'm cheating, but just so that you're aware, I'll give you some numbers if you want to check yourself. Coulomb's constant is 9 by 10 to the power of 9 by 10 to the power of 9. 9 by 10 to the power of 9. Charge of an electron is 1.6 by 10 to the minus 19. The mass of an electron is 9.1 by 10 to the minus 31. And the average radius distance between the proton and the electron, that I do not know off by heart, is 1 by 10 to the minus 10. That was the only thing that I didn't know off by heart. If you sub in those values, we get a value of 1.6 by 10 to the power of, is it 6? Yeah, 6 meters second. We get the speed of an electron to be 1.6 million meters per second. Hey, welcome in, Kib. Welcome in, everyone. Hello, Pep. Welcome in. It is fast. The electrons have zoomies. They do. 1.6. Nowhere near the speed of light, though. Nowhere near the speed of light. In my defense, the weather is it's fine. Don't worry. I was very late starting stream today, and I didn't realize, but Twitch had actually given me a front page slot that I applied for months ago, and they just didn't tell me, and I missed it. So, look. C'est la vie. C'est la vie. It is what it is. It is what it is. Furthermore, if we wanted to, we could calculate the kinetic energy of the electron as well. Kinetic energy is equal to half mv squared. You could sub in your values and you get it in joules, but something that I'll do really, really quickly is I'll just say that it's 7.5 electron volts. You divide by the charge of an electron. It's a unique unit that we use in atomic physics and quantum physics because everything is going to be 10 to the minus 19, 10 to the minus 22, 10 to the minus, actually it's not really that low, 10 to the minus 17. We keep saying these numbers over and over and over again. So in physics, we tend to use electron volt as a measure of energy with all of these things, just because it's way, way easier to use, easier to keep track of. It's not an SI unit, but we do use it. Classic Twitch, exactly. Great question for a particle physicist here. Love physicists making stuff. I mean, engineers made the whole field of engineering just for convenience. Okay, I shouldn't say that was mean. It's true though. Every field makes their own field convenient as they need it to. That's what models are all about. Making your model as simple as possible to make everything work. Okay, so we can calculate the velocity and the kinetic energy of an electron. Woo! Something bad happens though. Planck said a few things in the past. Said a lot of things in the past. Or it's also another guy who he based all of his work on was Maxwell, right? And here's a line I'm just going to take from a book. Maxwell's theory of electromagnetic waves predicts that an orbiting electron emits radiation, causing it to lose energy. An electron emits radiation. It is known, it was measured in some shape, way, or form, that electrons that are orbiting a nucleus will emit energy. Now, how does Earth keep the moon at its distance that it does, right? The orbiting mechanics, which is what we used earlier to kind of derive the force expression of the electron, the orbiting mechanics in this case are about the balance between electrostatic charge, in case of the moon and the earth, its gravitational force, and how fast it's going. It's quite literally moving so fast that it's missing the proton, in the case of the electron. But if the electron is losing energy, well, we know it can't be losing mass. It has to be losing speed. So if the electron begins to lose speed over time, it collapses. The electron will fall to the center of the proton. The same way, if the moon starts to decelerate and slow down over time, it will crash into Earth. Or the Earth crashes into it if it has a significant enough gravitational pull. This doesn't happen though. Atoms are stable. We exist. We have matter. We take up space. We're fine. Why? For the first time, it was almost impossible to really get classical physics to work. Quite literally, Lord Vader, you're absolutely right. Electrons cheat. This is the birth of quantum physics. It had to explain this. Why does this not happen? Because classical physics, Maxwell, Newtonian, all those physics equations can only work. And then came along a very important gentleman, and we're just going to pause for an ad break here. I want to talk about Bohr. He saves the day with his model. And make sure to catch the next episode on. Hi, Patrick. Welcome in. Welcome in. Hi, Ash. Hope you're keeping well. Hi, Spider. Happy Women's Day. Happy Women's Day, everyone. Well, then the positive and negative, you can imagine something moving that fast, as we calculate 1.6 by 10 to the 6, crashing into something is going to destroy it. So that is generally considered a bad thing. Well, you know, whoever you may ask, yes. So we're taking a quick ad break. And the ad break that we're doing, in case anyone is new to this community, you guys are more than welcome here. I teach physics and I play video games. And it took me almost 3 months, two and a half months, to finish God of War Ragnarok. So today we're doing a really fun thing where we spin the wheel, we take some crazy gambas, and we gamble all our, you know, life savings away. It's not real gamble. And we see what game I have to play next. And I want to spice up my choice. I want to play something addicting. So that is going to be my goal. Diablos, thank you so much for your prime. Shadow, thank you so much for your prime. You guys are very, very kind for subbing with your primes. Welcome in, welcome in. Factorio is on the list. Yes, chat. I want you all to say thank you to the gods of Kratos, because Factorio is on the list today for the first time. So we'll be back doing this quantum theory physics again. So I left you on a cliffhanger where atomic theory collapses. Rutherford's planetary model collapses quite literally, where the electron crashes into the proton as it emits energy in the spectral wavelength. So yeah. No, Kip. No, it's not. Not this time round. I was thinking, should I play Star Trek? Star Trek requires a lot of performance from me. As in, I'm going to be in costume and I'm going to do voices for Star Trek. So I can't do that today if we end up landing in on it. I think I might take a little break. But it's still a game I want to play. Yes, I am on Instagram. Tiny Toxic Tofu. You can find me on Instagram. Instagram is my biggest social media. If you're interested in it. I'm glad, Ash, you found the stream. Welcome in, welcome in. Yes, thank you so much for your sub. Really, really appreciate it.
Mine. A mine.
A mine. You're very, very kind for contributing your PP points. Thank you. You're very, very good. We're about to choose the games on Spin the Wheel. So let me screen share. And I'm going to look at my Steam. And we're going to choose all the games that are on my wish list. Sorry, not my wish list. What I'm trying to do is I'm trying to play the games I already own. Because, you know. Not really. I don't tend to play first-person shooter at all. In fact, I'm notoriously bad at shooter games. Yes. Yeah, so sorry. I do have a plan for Star Trek Voyager Into the Unknown. I have a plan of a couple of costume changes and voices. So I practiced Janeway by putting my hand over my throat. But I kept doing it. I hurt my throat over time. Obviously we can do a few people better than another. Neelix, oh god. I hope to lose Neelix as soon as possible. We hope to lose Neelix in Star Trek Voyager, but you know. Let me wait, where's my display capture? Okay, nobody send me something dodgy now. Am I right? Correct? No, that's correct. Window capture. Here we go. I found the button. This is it? This is it. Woohoo! Spin the wheel! You can also see that our last win was God of War Ragnarok, which is great. It's great to see God of War Ragnarok from the last time we played the Spin the Wheel. Okay, let me boot up my Steam and we're going to put some games on this list. I was born too late to experience... You know what, Lord Vader? I felt like that because I continuously tell my chat and my community that Star Trek Enterprise is the best Star Trek. Now, I keep saying that and everyone in chat like comes up in arms at me about it. But that was the Star Trek I grew up with. What's really important with Star Trek is to find the Star Trek that got you into it, if that makes sense. I think everyone has a Star Trek that they can associate with them. So, yeah. Okay, so here we go. Let's find the games on the list. Factorio is officially on the list. I'm sure everyone is bloody delighted about that. Ooh. I might actually switch to my programming overlay. Might be better. And instead of my code, put this up instead. There we go. Keep the list at that. Okay, let me find what other games I want to play. I have Against the Storm, Beyond Two Souls. Not too crazy to play that. Dyson Sphere Program, yes. Dyson Sphere Program. Fallout New Vegas. Nah, I don't have time to mod that today. Let me see. Boom 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 boom. Do I want to play Mass Effect? I think I need a shorter game than that. I want something addicting. Okay, we'll definitely go with RimWorld again. I kind of want to give it another go. RimWorld and Satisfactory. There we go. There we go. Bum 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 bum. Do I want the Wandering Village? I think this was a game I wanted to buy for myself. Let me look at my wish list. I'm kind of focusing on city builders, yeah. Should the games that have lost again and again have an increasing chance of winning? Ooh, that's an interesting comment. I wonder. Just looking through my wish list right now. Do you know what? I'm going to put Star Trek on it. It's okay if I'm not in costume today. I'll just be in costume next week. Fuck it. Let's do it. Star Trek Voyager Across the Unknown. If I land on it today, we'll start with it without costume. It's fine. We'll practice our voices and get the Voyager stuff. Exactly, exactly. I'm kind of feeling it, you know? But, Captain, that's a highly illogical choice. Let's look at what else do I own. Resident Evil Requiem, I'm keeping for my honeymoon. Don't ask questions. I'm playing it on my honeymoon. That's exactly... I kind of want to play Atomfall. Oh, except it's not on sale. No, I'm not buying Atomfall on full price. Nah, I'm cheap. No way. No way. No, I'm not going to buy Atomfall on full price. Yeah, I loved Raft. It's really, really good. Oh, I'm not going anywhere on my honeymoon, Kip. I wasn't joking. I'm staying home and playing Resident Evil 9 Requiem for my honeymoon. That wasn't a joke. I'm dead serious. I take my Resident Evil and Grandpa Leon very seriously. Hi, Finionat. Welcome in, welcome in. I want to give Prey another go. I rage quit that game, though. I don't think I have any other game that I really, really want to play right now, chat. I think this is it. I've never had only 5 games. Just checking one more time. Of games that I own. Pet the mods. Kerbal Space Program. I played Kerbal Space Program, yeah. I'm not the biggest fan of it. Streaming wise, it's too much. Too much. The new one is out already, I believe. It came out just the end of February. I know because I was at a conference when it came released. God damn it. You know what? I think this is it, chat. This is it. These are the only 5 games I want to play. I've never had such a limiting thing before. Yeah. So, if anyone is interested in how this works, is that we are going to start a new prediction. Which game will it land on? So obviously, vote for the game that you want to win, but also maybe just vote for anything. Because it doesn't matter, because it's an equal chance. Which game will win? Spin the wheel. Question mark. So is it going to be Factorio? Number 2, is it going to be Dyson Sphere Project? Number 3, is it going to be RimWorld? Number 4, Satisfactory. And number 5, Star Trek Voyager. Across the Unknown. Oh. Too many letters. Okay. So how long can we have this prediction running? I'm going to run this prediction for 5 minutes before we can start to spin the wheel. It's not a very long prediction, it's because I can't spin the wheel until you guys choose that. So I might take a quick break, pee real quick, grab a cup of tea, have a cookie. I'll bring a cookie in, and we are going to spin the wheel of the game. I'll start downloading in the background, and while it's downloading, we'll finish the lessons on quantum theory. Oh, the Invincible. Sure, I'll check it out. I'll add it to. Let me just look at the Invincible. You said that sounds like a lovely description for a game. I'll check it out now. Steam. Oh, are you sure that's the name of the game? Yes, it's last one standing wins, by the way. So we're doing this backwards. Oh, there you go. I found it. The Invincible. Oh, it's a huge sale on it. I have seen this before. Yes. Am I wrong in saying this that Cora played this? Was it Coraline who played this? No. Maybe I'm getting mixed up. I might be wrong. Tarek, do you remember if Coraline played the game The Invincible? It was kind of like a deserty planet she was stranded on. Maybe I'm getting confused though. Yeah, so this is last one standing, which means it's spin the wheel but backwards. Bear in mind. Bear in mind, it's spin the wheel but backwards. Alright, I'll be right back. Gonna make a cup of tea, grab a biscuit. We'll be back in a couple of minutes. Oh, I'll actually keep the wheel spinning so you guys can see the game. All right. I hope you're ready. I hope you are ready. This is the moment y'all been waiting for. Sorry, we need music. I know exactly what music we always play for this. Here we go. What? Oh, okay. I typed that completely wrong. Here we go. Let me stop the Skyrim songs. Let me go and spin the wheel. And customize. Volume 50%, spin seconds. Okay, here we go, here we go. Are you ready to rumble? And the first game to be eliminated in this round. Oh, is it going to be Satisfactory? Oh, we're slipping past. Is it going to be Star Trek Voyager? Or Factorio? It's Star Trek or Factorio. Star Trek or Factorio. Star Trek? So long. Live long and prosper. Factorio is out! Here we go. There's only 4 more games left. It's all or nothing. Slow saxes, we're getting the end. Oh, oh. Is it going to be Satisfactory or Star Trek? Oh, oh, oh. I'm so sorry. It's not going to be my wonderful voice acting in Star Trek. Live long and prosper across the unknown. My points! We are left with the remaining 3, apologies. Satisfactory, RimWorld, or Dyson Sphere Program. Are we oh. Skyrim's playing in the background. Are we ready to spin the wheel?
And they call it a mine.
Yes, Dr. Prince Bones! Welcome in. Thank you so much for the resub. Really appreciate it, Dr. Prince Bones. Welcome in, welcome in. Coming in a perfect moment for us spinning the wheel. Who is going to be eliminated and left for the last finale? I think it's safe to say it's Satisfactory. We are not satisfied with Satisfactory, and it goes! We are left for the grand finale. It is Dyson Sphere Program versus RimWorld. I will remind everyone that whichever one it lands on is the one getting eliminated. Here we go. Here we go. Here we go. Oh! Okay, it has to be RimWorld, right? It's not going to pass RimWorld, surely. Is RimWorld out? I think it's... not even a close one. Cheers. And so, lab rats and labradoodles and everyone in between. We have a winner, and it ain't actually RimWorld. We are left with Dyson Sphere Program. Dun 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 dun. Let me manage the poll. No, that's the wrong thing. Manage prediction, choose outcome, and the winner is Dyson Sphere Project. How many winners do we have? This is a science dance gambling stream. I'm a woman of many talents. I am indeed. I am indeed. Okay, so what I'm going to do is I'm going to go into my library and start downloading it in the background. Oh, it's a tiny game. It's only 4 gigs. Okay. I mean, city management games don't tend to be that big, to be fair. But still, I'm surprised. In case you didn't know, Dyson Sphere Program 1. Not sure if you guys knew, though. All right. Hi, Elming. Hope you're keeping well. Hi, Witch. Do we have many winners? Let's see the details. Oh, 65K goes to Witch of the East and Diablo. Only 2 people. Only 2 people gambled on it. Oh, damn. Oh, that's impressive. Big win, big wins indeed. Wait, go back. I need to vote. We'll do it all over again. Neji.
Precious.
What? That's 4 years. Oh my days, 4 years of subbing to this channel. Thank you so much, Jay. Ah, you're so good. Thank you. Thank you so much. In honor of winning Dyson Sphere Program, that's going to be the game we're going to play in a little while, an hour or 2. I am going to try one of the greatest cookies that is in Ireland. They're called SOS cookies. This is, I'm going to show it to you now. If anyone is fasting or, you know, anything like that, please turn away. I don't mean to tease you, just for a moment. This is a deep dish. Sorry, let me focus it. Deep dish. Ugh, stop focusing on my face. Deep dish Biscoff cookie. That's a slice of heart attack. Oh, it's so good. It's so good. Thank you so much for the resub. We have a hype train.
Red alert.
Oh,
All
wrong.
hands stand
Sorry,
at
sorry,
battle
sorry.
stations.
Choo choo.
Oops.
Motherfucking choo choo.
Wrong button. But there's a few people in here. Welcome in, everyone. If you, Dyson Sphere program downloaded. If you're just coming into the stream, if you're new here, we did our spin the wheel of what we're going to play. I'm not going to play God of War anymore on stream. I have downloaded it on my Steam Deck and I'm going to be achievement hunting solo without you guys. I'm sorry. I'm going to do all the side quests and stuff by myself, if that's okay with you. The second thing is that we are doing quantum theory. I'm introducing quantum theory. If you missed out on it earlier, do not worry. We're going to hit something new. Hi, Maureen. Hello, welcome in, guys. So don't worry if you missed anything. We're going to cover something new. And we did spin the wheel, and the game that we landed on is Dyson Sphere program. So in a couple of hours, we are going to be playing just that. So if you're interested, you're more than welcome to hang out. What is today's topic, madam? Perfect question. We are going to show you why quantum theory was introduced in the first place. Oh, that Biscoff is delicious. Let me try one more bite real quick. Just one more bite and we'll start teaching. That hurts my teeth. The amount of sugar there is not good. Not good for you. That's so good. Like, the center is way too rich. It's pure Biscoff and sugar. But the cookie itself is so good and moist and soft. Oh. So moist. Sorry. Got distracted. Let's talk about quantum theory. As we have a hype train happening on stream, let's talk about quantum. So, quick revision of what I said earlier. Rutherford came up with the planetary model of the atom. And so the electrons orbiting around it, and using classical physics, they were able to derive what the velocity and the kinetic energy of the electron is. But based on Maxwell's equations and Planck's predictions of quantum theory, or of this kind of realm of physics, is that, well, that can't possibly be true. Because we know electrons emit energy, right? And so if they're losing energy, it has to be lost via speed. And if it loses speed, the electron will collapse into the orbit.
Back on the menu, boys.
It will collapse into the orbit of the proton, and matter could not exist as we know it now. So this is where quantum theory had to be given birth to fix everything. Kaz, thank you so much for the 100 bits. You're very, very kind subbing in and giving bits today. You're very, very kind. Thank you. It's Girl Scout cookie season, and I've already I have a question to my American viewers. What is Girl Scouts? What do Girl Scouts do? Is that like is that the same thing as summer camp? And it's specifically a summer camp where you learn how to survive in the wilderness. Is that what it is? Would that be a fair description of Girl Scouts? We don't really have that here. Hi, Graham. Welcome in. Did you see the spin the wheel outcome? No, we don't have. No, we don't have that one. Nuke Nade. Keith, thank you so much for your resub. 8 months. Let's go. Almost a Twitch Baba. Thank you. It did hold up. The game that we landed on, I don't know if... I feel like you were egging this game on. Dyson Sphere program? Yes! Okay. Yeah, we don't really have that in Ireland. Or maybe we do and I'm just not around children enough to know. That was a very weird sentence to say, but you know what I mean. Anyways, it is what it is. It is what it is. Okay. Sorry, is my music playing? Skyrim, relaxing music in the background. Let's get cracking with quantum theory. So to fix this issue, we go back, I'm not going to go too much in this because that's a different topic, but it's to talk about the electromagnetic spectrum. So you remember that light is a particle and a wave. Okay, so we know that light is a wave. And the electromagnetic spectrum is a huge spectrum of frequency and wavelength. One increasing in the other direction, one increasing in the other direction. And the visible light is only like a little tiny part here, okay? But if you wanted to measure the energy of the electromagnetic spectrum, whether it be gamma, which would be super energetic, excuse me for burping, or it could be cosmic background radiation, where the microwave is on the opposite end of the spectrum. There's an equation that was developed by Planck, Planck's infamous equation. AE is equal to HF. E standing for energy. Sorry, one of my lights is kind of glaring right at it. This is energy in joules. H is Planck's constant. And F is frequency. So the range of frequency value of the electromagnetic wave is dependent on Planck's constant to extract an energy value out of it. This is really important. This means that the energy of the electromagnetic spectrum is discrete. So you know the two terminologies, there's continuous and there's discrete. It means that the energy can only exist in exact certain amount of values in ratio of H. Can someone remind me again? 6.626, I think it is, by 10 to the power of, don't remember. If anyone maybe quickly could Google it for me. I forget it myself now. 34. Meter squared kilogram per second. Is it not joule second? Am I wrong? Did I get my units wrong? Is Planck's constant not joule second? Could be wrong about that. Maybe they're both units the same. No? No, it's not. I might have missed my units. Google gave me that. Fair enough. I might be wrong. Bear in mind, my units might be wrong. I missed how this could be discrete. Why? Is the frequency is continuous. You're right. Frequency is continuous. But if you multiply the frequency by a discrete number, by 2, for example, every single time, let's say it's 2, it's really 6.626 by 10 to the minus 34, then no matter what number you put in here, it will always give you a discrete energy value. Does that make sense? By multiplying by Planck's constant, you will always get a discrete outcome in that case. I could be wrong about it. No, that's okay. It's weird because you are right. Like we say that the frequency is on the continuous spectrum. It's a spectrum. It's on the spectrum of light. But this guy H is always this number. So no matter what you put in for F, you will always get in certain levels of H, in certain ratios of H. It's always in proportion to H. It's okay if we're not getting it, that's fine. There's a lot of history to this. And quantum theory isn't exactly the most intuitive thing in the world. So you know what? It's completely okay. I promise you guys, it's completely okay. So when quantum theory came about, I'll just read a little bit of this part here, just for reference. So spectra show that under certain conditions, the photons emitted or absorbed by the atom have only certain discrete wavelengths or frequencies. This implication is that energy of an atom itself can only have certain discrete values. That is, the energy of the atom is quantized. That's where it comes from. So it can only exist in certain energy levels. So let's take an example. Do I have a diagram here? we'll say level 1 of the electron here, and we'll have energy, or energy of the photon. We'll say energy of the photon before we even talk about the electron. So energy of the photon is here, level. When we talk about the atom, for example, energy can be absorbed by the atom, and it can jump into a discrete level from level 1 to level 2. In that case, so energy of a photon is coming in, it's absorbing it, it's going into a higher energy level. The opposite can happen as well, is that energy can come out and it can jump from level 2 to level 1. The idea is it can't exist here. It can't exist here. It can't say, I need to go to the store, because let's say this is from your house to the store, and you really, really want to get to the store, but you decide to stop and exist somewhere else. You'll you'll stop at a single point. I think joule is equal to kilogram meter square a second, so joule. That's a good point, EKG, that derivation. That will work out then. Then our units are correct. I'm confused by, there's a few things going on in chat. I can't keep track of it. Apologies of a few of the questions. If there's a strict question, let me know. There's a few things going on at the moment. An analogy that I heard before for this is by Jim Al-Khalili. And the idea is that energy can only exist the energy value of an atom can only exist in kind of a building, in a big story house. You can live in level 1, you can live in level 2, you can live in level 3, level 4, or floor 1, floor 2, floor 3, floor 4, and so on and so forth. But you can't live in floor 2.5. And you might say, well, actually, Tofu, I could possibly end up there. I could be stuck halfway on the stairs. That analogy breaks down if you start to be very, very pedantic about that. But generally speaking, that's kind of the idea behind what they mean by discrete levels. There is no stairs. We get we get beamed between levels. Okay, there we go. We get beamed between levels. That's a good analogy there. And you can kind of do interesting maths with this, in the sense that, well, you could also have level 3. And this maths is very, very important for the 3 ladies that I've mentioned in the title of my stream. A lot of their work involves around this, where... where you could have energy level 1, energy level 2, energy level 3, and you could actually measure how, from where the electron drops down, or from what atomic excited state it dropped down. Because when it falls from energy level 3 to energy level 2, it will release a discrete amount of value of energy. Or if it drops down all the way, it would release a huge amount of energy. Or if it dropped from level 2 to level 1, it would jump down and release a different amount of value of energy. And it is discrete. It is a known value. And this monetarization actually became really, really important for a lot of fields of research. Radioactivity, extremely important. For Goeppert, her work as well became really, really, really important by monitoring these drops, because sometimes weird things happen. Some guys can do very, very simultaneous things, and other times it looks like it's simultaneous, but it really isn't. So there's all these little things to keep track of. So it does kind of seem straightforward and simple. That's great. But be mindful that this took a lot of commitment and a lot of work to show back in the day. Well of potential. Yes, Sash. That's right. We do use wells in that case. Now, there's a little bit more to this now that we're going to cover. Hi, Tetsu. I'm going to read a little bit of an intro to this. Quantization of angular... Oh, yeah, I suppose a small thing. These are called excited states. A bit of a definition. The higher energy levels are called excited states, and the lowest level is something called the ground state. So there's a ground state of where electrons are hanging out and chilling, and then there are excited states. So two things. We mentioned excited states several times before. It is not what you might think it is in the English language. There's a running joke, I guess. How do you get an electron excited? And then people, comment very, very inappropriate things. But just bear in mind that that's where the terminology, or that's the terminology we do use in the physics language. I just can't hide it. I'm about to lose my charge and I think I like it. Okay, so let me read a little section here for you. Central to Bohr model is the postulate that electrons can orbit at certain allowed levels of the radius r. But what determines these values? Bohr proposed that the orbital angular momentum, capital L, of the electron could only have certain values given by the relation L is equal to NH2 pi. So this is the introduction to Bohr's model, Bohr's theory. So we're going to talk a little bit about angular momentum now. Physics, we're doing the introduction to quantum physics here. It's okay if it's a bit advanced in the sense that you guys are jumping in the middle of the stream, and that's okay. Kind of hang out for the vibes for now. And I'm skipping a lot of things. For example, I didn't cover where force came from and where the centripetal acceleration came from. And we didn't cover Planck's story. So just bear with me. For now. So to bench Rifu. I'm not sure about that. All right, let me find the equation. The angular momentum, the capital L like this, of the electron can only have certain values. So the value is h over 2 pi, and it can only be in discrete levels. So kind of like we mentioned earlier, in energy level 1, in energy level 2, and so on and so forth. It can only exist in certain levels. We give this letter or this notation N. L is the angular momentum. N is the discrete value, the discrete level that it's in. And it has to be an integer. So N can equal to 1, 2, 3, so on and so forth. You can't have 3.67. You can't have, what would you chat put in? 69.420. You can't do that. No. Pi, exactly. There we go. We can't have those values in there. Not in this case, Grim. In other integer kind of stuff, you can, but not in this one. And not in this example. Exactly. N is a place, and L is that's, you know what? We'll take it. Okay. When we talked about the atom or the electron orbiting the atom in circular motion, we always go back to classical physics, because even though, we'll say things like that classical physics can't explain it. We do bring classical physics into this all the time. We bring this equation from classical physics of angular momentum. L is equal to VR. I know this. The angular momentum of a particle that has mass is speed traveling at a linear speed perpendicular to the centripetal acceleration v of an radius value r. That is the general equation for angular momentum. And similarly to before, how we equated the electrostatic equation with the centripetal force, we can equate the angular momentum of the electron that we stated earlier from Bohr's model, nh over 2 pi. Sorry. Now, our goal here is that we're going to try and find what the speed of the particle is. So let's rearrange the equation to find v on its own. I don't think we can cancel anything. V is equal to nh over 2 pi mr. Okay, are we in agreement that that's what v is equal to? Be okay. No complaints from me. We're going to be cheeky feckers. And we're going to go from the previous Rutherford model. We're going to extract an equation. Fuck. I lost my... Never mind. So, if you look back at the VOD, I promise there was an equation. There was an equation earlier we showed where v squared is equal to ke squared over... What did I say? mr. Remember we did that? It was when we equated Coulomb's law with the centripetal acceleration or the centripetal force. We said that earlier in Rutherford's model, and the model collapsed due to that. So there we go. We have this equation from earlier. Unfortunately, I'm running out of whiteboard, so I keep having to subtract some things. Welcome in, War. Don't worry, we don't stay serious very long. We're not a very serious channel most of the time. So, whatever impression you have of me, save it. It might not last very long. Okay. Then, what we could do is, we can make this v squared, square everything out, and equate those two equations then, because it'll just be v squared is equal to v squared. So let's do that. Let's say ke squared over mr is equal to n squared h squared over 4 pi squared m squared r squared. Okay. I hope we're keeping up. Always take a... Yeah, I always get my students... to delete... to take photos of my lecture notes as I'm writing on the board. Because sometimes I run out of space and I need space on the whiteboard to tell a story. And do you know what? I don't know about you, but when I was a student, it was very difficult for me to write what the lecturer was doing on the board and actually listen as well. In hindsight, in 2026, it's actually so nice if you sit back and just take a picture of the whiteboard and focus all your attention on listening and understanding. And then straight after class, if your schedule isn't too overwhelming, to write out notes from that lecture as well. Going back, that's the way I would have studied, especially for some of my favorite classes. That's what I should have done. But, you know what they say, hindsight and all that. So, what we could do is we could rearrange this equation to find r in its whole, the radius, the Bohr radius. That's kind of our goal. Hindsight is 2020, after all, it is. One thing that we can cancel, there is one thing that's in common, is r, the letter r. We can get rid of r here and r here. We're left with just one r on its own. Is there anything else I can cancel? Oh, mass! Is there any pies? No, I think that's all I can cancel. Don't see anything else. But we can rearrange the equation now to find r on its own. So let's do that. I'll just try and write smaller a little. If anyone's watching on their phone or tablets, I apologize. Sorry about that. Sorry, my music stopped. I don't seem to hear any Skyrim music. Will we put on some Mass Effect trilogy music instead? There we go. Good evening. Hi, Jimmy. Welcome in. Welcome in. How are you doing today? Ooh, Sunday roast. Nice. I spent the morning and afternoon cooking actually as well. I made sweet potato soup. It was delicious. And then oatmeal blueberry cookies. Very healthy. But I've been out the door a lot lately and I haven't had lunches. So I thought, you know what? It might be a nice little meal prep to do for the day. Okay. So we've cancelled a few constants off and we were looking for the Bohr radius. I'm kind of spoiling it, but we want to know what is the size of the atom, the radius based on the energy level that it's in. Because we know that it's energy level dependent because of that n value. Well, I'll show it to you now. Let's rearrange it. I'm going to do it here because it's going to be easier for us to do. So we have r on its own and bring it across is equal to n squared h squared all over 4 pi squared m k e squared. Okay? We're going to clean it up a little bit and we're going to leave n squared on its own. Let's do that. Over here, we're going to do r is equal to n squared. What we have in brackets here is h squared. We're not doing anything. We're just, you know, we can take n squared out in brackets. It'll just be visually easier to do this part. Oh, lads, my stomach really hurts. I think that was the cook. That deep dish cookie. Oh. Oh. It was delicious, but clearly is causing, yeah. I volunteer as tribute to test the cookies for poison. Thank you. Thank you. You're far too kind. So we have r is equal to n squared in brackets h. It's the same equation. I just pulled out the n squared out of there. Get this expression. And I want you to have a quick look at everything inside that bracket. Let's sit back and look at it. Let's just sit here and look at that. What's in that bracket, guys? What can we say about everything in that bracket? In front of the n squared. I placed it like that. Bang on. It's just a bunch of constants. It's just a bunch of constants. H is Planck's constant. 4 is a number. I is a number. Constant. Everything's a number. Mass of an electron. Coulomb's constant. Charge of an electron to be squared. All just a bunch of constants. This is a really important little part for his model. So this becomes Bohr's radius. If you've ever heard of this before, this is Bohr. Specifically, the story is that this is Bohr's radius for a hydrogen atom. So 1 proton, 1 electron. And you might be saying, well, why is it called for hydrogen? Because it doesn't really work for anything else. But we still use it. We still use it. So this is definitely a theory that was derived. There's a few flaws in it. I don't usually call out followers, but I really appreciate ground state following us, as we were talking earlier about ground states and excited states. It's great to see. Thank you. But where was I? Yeah, so there's a few kind of flaws in this theory. The way quantum theory tends to be taught is historically. There is kind of like a historic reason as to where things came in and why we added them and how they developed further. So when you study this, you do teach it incorrectly. It's weird because we don't really do that in mechanics or electromag or anywhere else. Instead, we tend to teach it. Quantum is taught quite historically, in my experience. Maybe I was the only one. Let me know. Now, should I bother with... I'm just going to look ahead. I want to skip over a section. I think I don't need to... Part. Pretty much zero, yeah. It is interesting, Volvo, yeah. There's a few interesting things. Radius is in the distant electron from the... Exactly, yes, that's the radius. Yep, that's what we mean by this. To start with functional. So there's a little part that I can skip over, which I'm kind of happy about. I'm going to skip over it because I want to get to the juicy stuff. And the juicy stuff, for me, in my opinion, is de Broglie. I want to teach de Broglie. De Broglie, as we call him. De Broglie. And it was kind of an important part as well. So I'll read a little section again from this book, just to kind of support this a little bit. Bohr's theory provided the first successful calculation of the frequencies of the spectral lines of any atom. But at first, no one knew why. What is the Bohr model telling us about the quantum world? Bohr's key assumption that the angular momentum of the electron is quantized was new. This assumption was needed to give quantized atomic levels, without which the Bohr model would have the same many problems as mechanics. De Broglie proposed that electrons and all other particles have wave character. This was the first stepping stone into quantum wave mechanics. Yeah, maybe you're right. Yeah, that makes sense, Charles. Because it's so BS sometimes. You need to explain where the BS came from. Okay. So, his name is de Broglie, if you spell it out, but it's pronounced somewhere in the vicinity of de Broglie. Or at least in the accent that I speak in. But what he stated was that every particle has a relationship with Planck's constant and momentum, wavelength associated. So the wavelength is equal to Planck's constant divided by p. Sorry. Kind of started looking like rho, which is a Greek letter, and that's not what it was meant to be. So lambda is equal to Planck's constant divided by momentum. Oh wow, what a name. This is where the wave-particle duality discussion comes. The orbital radius is not allowed in a Bohr model. But in this situation, we can do it. What we're trying to achieve, or what we're trying to show, is if we look at an atom and we look at this orbit, it has basically a wave association. Am I in the right picture? Yeah. And depending on how many waves that could exist in it is directly proportional or associated with radius. Depending on how many waves exist, pretend they're supposed to be evenly distributed, have a different distance r from the center of the nucleus to the electron. So, what's the circumference of a circle? An energy, well, 2 pi r, and we're saying it can only be in discrete levels of wavelength, because you can't have a half a wavelength. Think about it. If I draw out proton and electron as in a stable standing wave, we're assuming that, yes. If we draw that out, you can't have a particle going like this and then like that, and there's a cutoff point. It has to be a stable wave. So in that case, the wavelength, the length of one wave, has to be an integer of the wavelength. As in, like, if you're trying to complete a full circle, it can only exist in a discrete number of those wavelengths. That n value comes back. Well, we can do something here. We can sub in this guy in here, couldn't we? We can sub in for lambda. So that becomes 2 pi r is equal to nh over p. P is momentum. Maybe we remember the momentum equation from classical physics? Hopefully we do, because we can substitute for it. N is equal to n over h times m over v. We're getting some interesting letters. We have 2 pi r, we have an n and a h and an m and a v. It's starting to look a little bit familiar. It looks very, very similar to something we studied before. Wait, where do I start with it? Rearranging and noting. Oh, right, I see. So now that we have this equation here, let's look at this part and look at this part. We can rearrange it. We can say NVR, move it across, is equal to NH over 2 pi. I've just rearranged these two parts of this equation, okay? So I put M and V from here across. They're being multiplied by R. We put 2 pi across. Because it was being multiplied, it's being divided on the other side. Hold your horses. This looks familiar, doesn't it? This is Bohr. This is what Bohr said earlier when he equated angular momentum of classical physics with his quantum theory. Using waves instead, we're able to extract another very similar, the exact equation out of it. Most confused if V is radial or absolute speed. It's linear speed. Always linear speed. If you use V, because usually you use V in just normal equations of motion, in straight lines and so on and so forth, it stays that way exactly the same. V is always linear. This was a really important step. Now, it's not perfect. There's still issues. So let me chat with you a little bit about the problems and the issues, other than, you know, our mental state at this rate. So this was really inspirational, that people were getting the same quantization states using different methods and different ideas. This was fantastic. This was, oh wow, okay, we have some sort of explanation. We still don't know why it worked, but it works, right? It still works. And Bohr's theory was found to work well only with a single electron present. So basically, as soon as multiple electrons got involved, shit got serious. It didn't work out in the well. This model does not, however, correctly explain the properties of atoms or ions that contain 2 or more electrons. Physicists eventually concluded that the Bohr model is not a correct quantum theory, but rather a transition theory. That's what it's referred to, a transition theory, that helped pave the way from Newton's mechanics to modern quantum mechanics. The Bohr model was very useful, it has very useful insights into why an atom has quantized states, but the correct quantum theory contains even more radical ideas. So we teach this, and we do maths, and you do a lot of solutions and solving using these methods, but it's not the answer. And this is where, again, I always try to kind of elevate and always remind that everything in physics, and everything in any field of science, by the way, that you study pretty much, is just models. They're just models and systems to make them as simple as you need them for your story. And that's exactly what Bohr did. He was working in this field. It was very, very, very difficult to understand it. And so he started simply. Work with a very simple hydrogen atom. It could work with the lithium and helium atom as well, as long as there was only one electron orbiting. But basically, shit, you know, yeah. It all went downhill after that. I saw the joke earlier, JJ. I didn't get it. I'm so sorry. I didn't know if it was mean or not mean, and so I decided to ignore it. Apologies that I didn't read it out. I didn't get it. Sorry. Niels Bohr. Yeah, that's his name, Niels Bohr. V is for velocity. It is linear velocity specifically. So angular is how much the angle of you changing, how much the rate of change of angle, while linear speed or velocity is rate of change of distance. Two different things. Speed is meters per second, how much your distance changes per unit time, while rate of angular momentum is how quickly that angle is changing per unit time. Two different concepts, but it is hard. I think there's really good GIFs to show, like animated videos to show the difference between them, and I think they're very, very handy. It takes a while to learn them. So there's different angular velocity is usually omega. It's a drunk looking W. Eta and over t. That's one of the ways we can get the equation. How this angle changes per unit time. Drunk looking W or a butt. Okay, fair enough. It's a butt. The butt. I'll take it. And V is equal to omega R. That's right. Leave Norther out of what? Sorry. Never heard that description of omega. She didn't work in quantum theory. In atomic and quantum theory. So we're doing quantum and atomic theory today. There's a lot more women other than the 4 ladies I mentioned on my list and Emmy. There's a lot more other women, but it's specifically for the theme of atomic theory. Hi, welcome in, NS. N is just a number starting from 1, 2, 3, 4, 5. You know, like it's an integer value of 1, 2, 3, 4. It can only exist in discrete levels in that case. What do you mean? She worked in a lot with Einstein's theory of relativity, specifically in what she's really famous for and what she did amazing work for was in general relativity. We're not covering anything on general relativity or Einstein today. The only atomic theory I know is Tom and Jerry. Welcome in, Tarek. So, from here on in, we say it's an integer in this case only because I have a feeling that there's a case where it is an integer, where it can exist negatively. I might be mixing them up with orbital. Yeah, is there something like it can be an orbital quantum number as well? So in this case, other than in this specific story, n can be an integer. The Radium Girls were a bunch of women who were hired to paint one of the arrows on watches and clocks in radium before it was publicly known how dangerous radium was. And so what they would do is they would lick their paintbrushes with a little bit of radium on it to get a really nice, you know, good stroke of radium drawn onto the watch. And so they infamously were exposed to so much radiation that they all died, and it was quite gruesome deaths. Those were the Radium Girls. It was very, very sad. I think there was, if I'm not mistaken on the story, there was a bit of a cover-up as well. That was kind of the little lesson that I had planned for today. What's the symbol to the left of pi squared? 4. That's the number 4. I streamed for 11 hours and 45 minutes. That was the goal yesterday. 11 hours, 45 minutes. But didn't you say no numbers? That's true. I did say that we were going to deal with no numbers. And there is a 4 in there. But that's only because 2 got squared. The only reason there's a number in there is because we... Yeah, because... That was not my choice. It just happened. 16-minute shorts. I know. What if we did A is equal to 4? True. I mean, technically that's what pi is. And I mean, all those symbols are just numbers. Planck is just a number. 4 is just a number. Pi is just a number. M is just a number. K is just a number. E is just a number. Two Got Squared would be a great band name. It was all numbers all along. It was a lie. It was a lie. No, none of them are variables. No. Planck's constant, mass of an electron, Coulomb's constant, charge of an electron, pi. No, they're all constants. They wouldn't change. I think this is a nice introduction to quantum. It is a bit much. There was a lot of moments of just trust me, bro. But yeah, just be mindful. So that equation is Bohr's radius, and this equation is I don't even know how to call it. It's proof of Bohr's quantization using wave physics. I don't know if that helps or makes things worse. I don't know what it's actually called. It's just when linear momentum equates to Bohr's angular momentum. I don't know if there's a name for it exactly, but that's the description of it, if that helps. We could use H bar, yeah? Oh yeah. I wonder why I never used H bar. It's quite a common one. Angular momentum. Angular momentum, yeah. H bar is H, which is Planck's constant, divided by 2 pi. And we just use a symbol like this for it. Like that. H with a bar. And the reason is because we use it so often. H over 2 pi, H over 2 pi freaking shows up everywhere. It's so annoying. Even there, it's H bar squared. It just comes up so often that people want to be lazy and shorten it down. It's the same why we have electron volts, because by 10 to the minus 19 joules, by 10 to the minus 16 joules, by 10 to the minus 14 joules is just so annoying to say out loud and make the mistake every time. We just convert everything to electron volts to keep it into a unit that we can use a lot easier. In my work, oh no, I wouldn't use, I have no quantum work in my work. Very little. There was only one little bit of atomic work in my work, and it was only theoretical preposition. Yeah, very little. None. I would say none. Nilch. Negligible in comparison to the rest. So I would just use SI usually. Yeah, I would use SI, which is kind of controversial. I tend to stick to SI units. And so it's quite hard sometimes to publish in cross interdisciplinary journals, because people will be really mean and say, that's not the proper unit. Sorry, I'm putting on a voice and being sassy, but in my experience, certain journals, publication journals, can be sassier than others. Yeah, sure, whatevs. I'm so sorry, we lost like 4 boards before this. That makes things worse or better. Is it? Oh, Jimmy, Jesus. I don't even know how to answer that. True, Nightshade, true. I know NASA wasn't using SI at some point and people died because, I don't know about people dying, but the story goes, it wasn't actually NASA. NASA gets a little bit of shit sometimes, but it was never NASA, it was Lockheed Martin, if we're talking about the same story. So, NASA can't make everything. They do delegate a lot of their projects, or parts of their projects. And so if you're referring to the Mars thing, and there was another incident recently, by the way. If you're referring to the Mars thing in 90-something, 99? One of the Mars probes basically crashed, or they lost it. We're not sure, actually. It could come back to us someday. But basically, NASA was using SI units. And Lockheed Martin was using, what's the Freedom units called? Imperial. And they didn't realize there was miscommunication, and that's why they lost the orbiter. It was like $9 million wasted, or was it $1.9 million wasted? Anyway, someone must have gotten fired for that. And quite recently there was on the news, one of the satellites that Lockheed Martin was working on with NASA. Can someone correct me on this one? The panels, the satellite panels were 180 degrees off. I was reading the article, I was like, oh, someone just lost their job. So the Mars orbiter thing was in 99, and the thing that I just mentioned was like just 1 month ago, I think. Not sure. Someone needs to add to that. That could have been, you know, a stretch of a story. Who is the most bizarre scientist in history? Ooh, great question. Gamow was known to be quite eccentric. Gamow was quite crazy at moments, but he was just eccentric and outgoing and flamboyant. Newton has a lot of stories. Brand comes to mind just of how bizarre and committed he was into looking for philosopher's stone. I tell the story all the time of how he discovered phosphorus, and Brand would piss in buckets, and he would also collect the piss of many, many men from his local pub, take loads of buckets of it, and store it in his house, and let it marinate for weeks. So yeah, that's commitment. That's commitment. Quite bizarre. Yeah. I'm trying to think of any other stories. And then what? Oh, he did a whole like bunch of distilling projects with the piss, and he would like, you know, with a Liebig condenser, he would marry, not marry. He would heat it. It would condense. He would distill it. He did a few other processes with it, and out of it he extracted a very luminescent, glowy liquid, which is now known nowadays as phosphorus. And a lot of people believe that this was the initial recipe or stepping stone for the philosopher's stone. And he died with his secrets, you know, he didn't want the world to know. But I think it was Boyle and Newton and other people discovered his secret recipe anyway over time, so people find out how he did it in the end. He was married, that's right, Hax. He was married to a widow, a very rich widow, who funded his projects. I remember saying this joke a couple of months ago. Gentlemen, you are not living to your fullest potential. You must marry a rich lady and do research in piss. He was actually taking the piss, Science Bish. He was actually taking the piss. Sorry, Nightshade, your comment got flagged. I allowed it. Hello, your videos helped me in electronics. Ah, thank you, Tammy. I'm glad to hear that my YouTube videos helped you out. Glad to hear that. Yes, exactly. One is using Bohr's theory. This showed Bohr's theory. So sorry, we missed it. It was a whole thing. There was a conclusion there. And then we did it another way. And then we got Bohr's radius out of it. But then we did it another way using De Broglie's wave theory. And we got the same answer. 2 different ways. That was the really cool part. What did they do to said piss? Wouldn't you like to know? Ronan, welcome in, welcome in. We're just talking about Brand. He was a famous chemist. And in the process of looking for philosopher's stone, he discovered phosphorus by distilling piss that he would collect from himself, I'm sure, and from his local pub. And he would ferment it, allow it to ferment him in his house. How do you write these names? Yes, sorry. Whose names? Brand. Oh, sorry. Okay, if you want the piss guy, this is his name. If you want Bohr, it's like this. If you want De Broglie, this is how you spell De Broglie. It's De Broglie. But you pronounce it De Bro. You know, like a bro. There we go. So those are the names of all those people in case you're trying to look it up. Your lambdas are peculiar. Are my lambdas that weird? I think there's some normal looking lambdas. I have nice lambdas. Don't shit talk my lambdas. I have nice looking lambdas. He is French, exactly. So in English, looking at his name, you would think it's de Broglie. So, but because he's French, it's de Broglie, I think. Well, again, I'm speaking with an accent. It's closer to de Broglie. I don't know if he asked people to piss in a cup. I think he might have been sneaking into the pub and stealing the piss from the buckets. To be fair, he was looking for the Philosopher's Stone and so on and so forth. You're coming in a bit hot with that message, but you know what? We'll take it for today. I did finish the nuclear physics aspect to it. Almost nuclear. Atomic theory. We did a bit of atomic theory. I hope that was interesting to some of you. It's not my funnest thing to teach, quantum. I don't really like it, especially past this point. Well, no, there's a little bit more interesting stuff. There's a few theories on multi-electron theory that isn't too terrible, but it's kind of in the realm of chemistry. But basically, from here on in, quantum gets very bullshittery. At least there's some classical physics here. After a while, it just doesn't become very fun. So, well, to me. So, look, I did it. We can put it down pen to paper that Tofu did teach us a little bit of quantum theory, or at least an introduction to quantum theory. But bear in mind that everything I taught you isn't true. Sounds a bit weird. It's a model, and it works fantastic for an atom that has one electron. It doesn't work much better than that, unfortunately. But, you know, Bohr's students went on to do amazing work. Heisenberg and Pauli, although I don't remember if... But they were all the younger, the next gen. They were the next gen students. I don't know if they were directly with Bohr, but they worked with him. So Heisenberg, Pauli, and another third name. Slipping my mind. But yeah, they all started working a lot heavier in quantum theory. Ah, electroplating chemist. Cool. I did a lot of electroplating myself. Sure, I could do some stuff on time dilation. I need to revise it again. It's been a few years. Yeah, I could do a bit on... It's not too difficult. It's not too... So with time dilation, the reason why I've been avoiding it is we need to talk about relativity. There's a few stuff we need to do, some Galilean relativity, and yeah, we basically have to start with Galilean a little bit before we get to it. It could take a while. It might not be a bad idea. I do need to revise it though. It's been a few years. Which brand of physics is your favorite? Thermodynamics. It used to be anyway. I used to love thermodynamics. I'm really into electrical theory, if that makes sense. Electronic devices, DC circuit analysis. Actually, I don't find circuit analysis interesting anymore. I've learned it. I've learned everything I need to know. I'm not interested in it anymore. I'm still interested in electrical devices and switches and flip-flops and latches and how they build towards a computer. Still into that. But yeah, thermodynamics would still be my favorite. If I could teach a subject and create my own subject, it would be thermal physics. Yeah, I teach a lot about capacitors. Like nanotech? No, so more so like applied. I don't mind teaching theory, but I like looking at complex system and working backwards to the foundation, starting from let's say solid state physics, like from electron hole theory and so on and so forth. Actually, not build backwards, build forwards. It's easier that way. Yeah, to me that's very, very interesting. No interest in high energy physics at all. Yeah. Absolutely none. So like everything that's trendy on the internet in terms of physics, I'm not interested in it at all. I'm not sure why. I guess I was a student and I was very interested in it when I was young and it got me into physics, but that wasn't what made me fall in love with it. Be warned of that game. Matastuxi, thank you. We're going to be playing Dyson Sphere Program. I hear that's addicting as well. Electromagnetics, yes. Not so much microwave electronics, though. Not that I just don't know enough about it to talk about it too much. Nothing wrong with following trends. You see, the thing is, I kind of got sick of watching videos and educational stuff where quantum physics and so on and so forth. Sorry. Thank you, Tarek. I was just... startled by a comment. Apologies. What was I saying? Can someone remind me again? Thank you, Tarek. What about quantum? No, nothing. Microwave electronics. Yes, sorry. I don't know enough about it to comment whether or not it's interesting enough. I haven't done it. Does that make sense? Oh, I'm so pissed off about that front page thing. God damn it. Sorry. Earlier, right before I went live on stream, I saw a post saying, your promotion on the front page ended an hour ago. I was like, what? Apparently, a month ago, I applied for a special women's thing idea, and Twitch never told me I got the front page. It lied to me. It didn't tell me. Oh well. Okay. What we're going to do is we're going to take a quick break. I'm going to make a cup of tea. Maybe alcohol, I'm not sure. Oh my god, it's 6 o'clock already. I started so late today, to be fair. That's my own fault. And what we're going to try and do is... we're going to build a cup of tea, build a cup of coffee, and we're going to boot up for the first time Dyson Sphere project. Do you know why Night in Danger? I don't know about that. Because it all happened after she died. So she lived not knowing what happened. And I know that sounds kind of mean, maybe, from one angle. I think other people are more upset and unfair and angry. Does that make sense? The people who live and knowing these things, it's a bit more upsetting. But she lived her life without knowing, so... yeah. Sad that she died so young, though. That's definitely sad. Yeah, I kind of wonder, is it better to die not knowing? And I know she had a lot of... yeah, but... I don't think there's anything after death, so... it's not like I think that she's in a ghost form and can look down and see what happened, so... you know... unfortunately, the story of Rosalind Franklin is not the only one. Then one to... what if she is a ghost? What if she's the one who's haunting me and it's not Maxwell? I've been given out to Maxwell's demon and it's never been Maxwell's demon. All right, we'll be back in a couple of moments. If anyone was interested, I wonder if the physics is good in Dyson Sphere Project. I hope so. I hope so. I'm interested to see how we get on with it. I'll see you guys in a little bit. Bye-bye. Bye-bye.